started. Today is October 3rd, 2018, correct? Okay, I got that one right. So this is ECE 3030. This is the first midterm review. So we're talking about all the foundational semiconductor materials. Okay, we're not getting into the devices yet. That's going to be midterm 2 and the final exam. So we're not really into the device mode. It's semiconductor materials and devices. So this is the materials portion, which, as you've seen on the Carmen canvas, is kind of a legacy of the ECE 331 class back when we were under quarters. So these are the 4 segments, the 4 slide decks that I said were going to be part of the exam. What I wanted to do is go through those very quickly. There is a 5th one that I was going to reveal, kind of point out, was on Carmen. We have these 4 segments, 1, 2, 3, and 4. Now some of these are set up for the take-home problem that you're working on right now with the diffusion. So some of this goes into more detail than is really necessary for this examination, for the preparation for the exam. So there's a 5th PDF that you should take a look at, and I will try to go over that very quickly as well. And I made reference to it. So as we get into the lecture material of the device portion, 432, we just started the exam, the lecturing on this right now, this week. But I just wanted to pull your attention. Here is a review of that 331 material. So this is the distillation of the 331 material that's going to be on the exam. That's really really key. So I want to go over that again and make sure, because there's maybe a few slides that are swapped out a little different. And you'll see a lot missing, such as the gory details on diffusion and oxidation. So download that as well. So let's start from the beginning. Okay. So I've got the 5 segments all ready to go, so we can kind of do this quickly. Oh, see, there's the Internet Explorer links thing. Oh, that first one I had open already. Okay, so here, Control L. So let's do this as a format. Let me go through the slides, but interrupt me if there's a question. If something is like, please explain that. Let's just do it right then and there. And if you don't understand something. But then I'm going to go through the whole PDFs, and then I'm going to open it up to questions. And maybe I've exhausted you by then. I took my dinner early, so I can do a marathon with you right now. And so I'll just open it up to questions after that and see how it goes. So let's go through. Okay, so this is just set up for where we're going. We're going towards this transistor story. But all you're supposed to glean from this is starting to get to the idea that the crystallography is very important, and the stress and strain. And once we go into the effective mass and mobility and things like that, you're going to see how by compressing and stretching the lattice, that alone is changing the physical properties. So this is one of your structured property relationships, by the way. Hint, hint. So here is the oxide. Okay, so we talked a little bit about the oxidation, but this is going to come up when we talk about transistors. So that's why this was important. I'm looking at oxide thickness and how this happens. And what's the unique property here at this interface?
Insulation?
Huh?
Insulation?
Well, this is an insulator. Yeah, this is an oxide insulator. But what's unique about that interface? Huh? Ah, yes, it's a virgin silicon, right? Remember, because it's oxidized from the outside in. So this is This has never been exposed to the contamination. I don't care how clean your clean room is. There's always going to be some sodium vapor, something in the air, aerosol, something. Maybe you can get rid of the particulates, but you're not going to get rid of every contaminant. And so therefore, this is really clean. And so that's one of the things. We'll get into that more deeply when we get into the transistors. But I wanted you to understand the material science behind this. And what's the second thing associated with this? Assuming it's not declared here, but what can you assume is probably, you heard me say it before. This is what crystallographic direction? Stefan?
I think it's 100.
It's 100. Yes. Because when why is it 100? Because just to give an answer in Berger's class is not sufficient. You got to tell me why. Why?
The lowest planar density.
Boom. Lowest plane of density. Therefore, so all those dangling bonds, which we'll get into later with the transistors, all those dangling bonds, it'll be fewer, right? Because there's some that are stuck in that SiO mode, right? Because it's a two-step process to go from silicon to SiO to SiO2. So it's, some of them are trapped. Okay. So this is, no, yes.
So back on the other slide, is it, what is it that was the 100 direction? Is it
The substrate. So if I bought a bin of wafers and I ordered it from the vendor and then I started to put it through my Intel factory, you know, I bought those wafers are 100. So then that would be this plane would be the 100. So the transistors are sitting on top of the 100 plane. That's the dinner plate that you're sitting on. So then this is just kind of seeing the big picture, not really 30-30 type of testable material. And you know, these are more of the applications and so forth as you get in, and the integrated circuits. So I'm not going to be focusing so much on this, but material properties, crystallography. Okay, so let's get to something interesting. Okay, I dragged you through a lot of bonding and chemistry and stuff. What are the important takeaways here? The important takeaway is that these traditional semiconductors are covalent bonds and directional. Who said directional? Yes, gold star. Directional bonds. So, you know, you have to have some understanding of the valence band structure and so forth, because this will become the genesis of where we get the forbidden energy band gap. But this is not a chemistry exam. So I'm not going to make you write this out to the valence electrons or do any of this, so forget about that. But there is something starting to be important here, is that it's starting to show you not only the distance of the electrons from the nucleus, but it's starting to lead you to understand what are the interatomic spacings, right? So not only is it a directional bond, but it's going to be a preferred distance where the repulsive and attractive forces, here this is energy, but you can also plot it as force, I think that's the next slide, ends up with this preferred distance. So this would be, you know, the center of one atom and the center of another atom, and that gives you the interatomic spacing. So that tells me when I build that lattice, what's the distance between the atoms, right? So this is looking at potential energy, I thought there was another one that was force, but yes.
Is a directional bond an ionic bond, or how would you define that? Okay, so it's only a covalent?
Yeah, ionic you can put it, so Classic is sodium chloride. So you can have a sodium and you can put chlorine like on any side. Right? But the carbon is like a certain direction it's going to be. There's the energy, same thing. Energy. Okay. This is kind of relating to the structure property a little bit. I guess there's not really a takeaway property. You're getting larger crystals, so that's the structure. I suppose the property, that's a little more like making a better jet turbine engine, so I guess that doesn't matter to us. We want electrical takeaways, so our takeaways might be something like this one, which would be the optical difference, right? So here's a single crystal of aluminum oxide, so sapphire, that's sapphire by the way. So a single crystal is clear. When it's polycrystalline, it's a little bit translucent and even has this porosity, but also even just the light transmission, it's very, very opaque when it's polycrystalline. And it's changing its porosity, so all these different things are changing. The one I kind of liked was that liquid crystal display where I'm actually changing when I go from a amorphous silicon. And why is that a silicon amorphous? Because it's deposited on that glass, which has no crystallinity. Right? So what is the difference between epitaxy and deposition? Huh? Yes. Yeah, so it's the temperature. So deposition means that everything, the atoms come down and stick, and epitaxy is giving that third temperature. It's heating up the substrate. So the atoms have an opportunity to move around. I mean, right, when we play Jenga, they just come down, and wherever they hit, they stick. Well, that means you lose Jenga pretty quickly. But what if I could take and I could hop things over? Like, that's what epitaxy is. So then they can hop into those little holes and fill things up, and then it's crystallographically perfect. So that giving that third temperature, the substrate temperature, heating the substrate allows the atoms to move around and minimize their free energy. And so this is amorphous silicon, which is usually the alpha. And that means it's just like through silicon onto the glass like spitballs, right? They're just going to stick wherever they land. And then here, they laser annealed it, maybe like that Nobel Prize that we heard about just recently, and somehow with a very high speed laser was able to heat up the silicon and make that melt and then recrystallize slowly, so that it could become more polycrystalline, and then the mobility goes up, right? Because the greater the crystallinity, the less scattering. So then I was able to make, so you're able to make a transistor driving that pixel smaller because the mobility goes up, and therefore that pixel allows more light through, right? Because this is where the light goes through. The silicon is, you saw the wafers I passed around, they're opaque. You can't see through silicon. So that's a good structure property, maybe one of my more favorite ones that you've learned about so far. So there's different preferred energy. So yeah, here's the one I was looking for. This is so it doesn't matter whether you're really looking at it as energy or force. They all end up with the same result, is that the forces balance, and the forces are zero where they balance each other, where attraction and repulsion balance, and that's the same preferred distance as when the attractive, when the energy is minimized. It's saying the same thing. So it doesn't matter which way you give your explanation. It's the same end result. So, lots of crystallographic systems. I am not going to be expecting you to draw you know, crystals on pieces of paper or anything like that. That's why I find the homework very complimentary. So don't expect that you're going to have to come with a drafting triangle and drawing crystals and vectors and things like that. But you know, maybe understand these are your three classics. Building blocks, the simple body-centered cubic, face-centered cubic, so be able to, you know, explain those. But really, the more important ones are, and again, things like packing, density. Other than knowing the 100 planar density is the lowest density for most of the planes in silicon, you're not going to have to know these kind of things, but for the exam. But let's fast forward past that. Yeah. So anything that appears in red is probably, you know, one of the key setups, right? So covalent bonds are directional, and so that comes from the sp3 hybridization, right? The S and the P coming together, leading to a directional bond, and because it's a directional bond, it leads to this silicon atom has to be 109.5 degrees away from this silicon atom, right? The location of that atom is precisely defined by the presence of these three atoms. I know it precisely, right? And so this has to be as far apart from these others because they're all coulombically repulsing each other, right? There's a big electron cloud here, big electron cloud here, big electron cloud here, big electron cloud here. So they're all pushing away each other. So, so that sets so now I've set the interatomic distance by the chemistry, and the bonding has determined and the directional bonding has determined the direction, and so everything's set. So that's our building block. So any perturbation on that, remember this is the diamond lattice, so it's two FCCs interspersed. Maybe this is the better one. So here's an example of what? What semiconductor would be representative of this? Huh?
Silicon germanium?
Silicon and germanium, yeah. This is the elemental ones, where it's all one type. And then this one is the, now you can say it. Yeah, the gallium arsenide, yeah. So this is the diamond, and this is the zinc blend, where you got the two different. And then it's easier to pick out where the extra four are, because they're a different size, a different color. You can see that that's a projection of that, that's a projection of that, that's a projection of that, and that's a projection of that. So how would you explain that in words? What is this? Stefan?
You can say it's like two zinc or two FCC lattices combined, where the primary one is like the gallium and the secondary is the arsenide.
Yeah. And can you get even more slightly mathematical?
All the the arsenic ones are A over 4, A over 4, A over 4 from the FCC.
Yeah. Yeah. So they're transposed by quarter, quarter, quarter. Yeah. Yes.
Which did you say was like the primary FCC?
Oh, it doesn't matter actually. You can. Yeah, it depends what your perspective is. You can think of the gallium being in the arsenic, or you can think of the arsenic being in the gallium. Right? It's 50-50. It's coin toss.
Okay.
Is that your question? I'm not sure.
I think, yeah.
Okay. Okay. So we've set the distance, we set the direction, and therefore this is going to cement what our band gap is, because we're going to go through, by the way, this is how you know it's 100. You would know it's 100 because they would have machined it to have these flats. But this is, I'm not going to really probe this. I don't think you should have to memorize this for an exam. It's not really, it's not going to help you understand the technology. So skip past that. Do want you to understand ways, okay, so a little bit, if we have these materials, how do we know what we have for these materials? And so if we grow an epitaxial crystal, then maybe X-ray diffraction would provide a way to interrogate. So if we use a wavelength, X-rays are very, very small, so their wavelength is commensurate to the interatomic spacing. So therefore it can sense that, right? And so, by the way, is anybody interested, this is just an off-the-cuff straw vote, but is anybody interested in taking the solar cell lab next spring? Was it too early? Okay, good. Yeah, we're trying to improve upon that this year. And then next year, we're considering, maybe I'll just throw this out there, but we're considering revamping the 5037 lab. And one of the things the students you might do next fall is make an LED and make a high-speed transistor. So it could be that you actually go and observe the MOCVD growth of the LED stack, and then you would go upstairs. And the reason I'm saying this is you would go upstairs to the 3rd floor and you would do an X-ray diffraction of the crystal that was just epitaxially grown on West Campus, and you could verify its crystallinity, its diffraction pattern. You could determine, here's maybe more representative of an X-ray diffraction. And you could do X-ray diffraction off of that actual crystal, and that would determine whether the growth was satisfactory or not. Because you're not going to go through all that labor and time and expense of doing microfabrication of an LED if the wafer is flawed from the beginning. So it behooves you, and I didn't emphasize this enough before, but this is a non-destructive test, right? So you're not going to destroy the crystal, you're just going to hit some X-ray. It's just like going to get your, when I broke my ankle playing volleyball, right? I just get an X-ray on my ankle and I'm okay. It's not harmful. And so it's a non-destructive test. And so here's some X-ray diffractions. This is more of an iron or something like that. But you're going to get a diffraction pattern. And so that might be something that you might be able to do yourself a year from now. And so here's that kind of structure-property relationship. Well, looking at the diffraction pattern, you can therefore determine, well, this is only partially a structure property because you're seeing with the X-ray diffraction what the structure looks like, but it's not really revealing to you the property. The property is more like that liquid crystal display where your mobility is changing. That's a property. I'm not sure I would say the diffraction pattern is a property. I'm looking more for the what an electrical engineer needs. The electrical engineer needs optical properties, the electrical properties. Okay, so now recognize that there's all kinds of point defects, line defects, planar defects. So a lot of things can go wrong, right? You build your Jenga tower, and maybe there's some defect in there. I just heard something on the news. Some skyscraper has a broken window on the 36th floor, and now they're wondering. And the building already sank 18 inches. Now they're wondering what's the structural damage? What's the integrity of that structure? Because if a window's cracking on the 36th floor, it means there must be some stress and strain and some twisting of the whole structure. And is it likely to fall down? Windows don't break for nothing. And so if it broke under stress and strain, and they already know it's sinking in the ground, so here's a point defect. This is what we now call anti-site defect. That's what I kind of presented to you today for that low temperature gallium arsenide for picosecond sampling. This is an interstitial, so this could be that boron atom that's trying to find its way to a substitutional spot. So this may be the guy on his way, on his hunt, and so that boron is an interstitial diffuser for your diffusion computer problem, and he's looking for this vacancy. And once he finds there, he's going to be quite happy because then he can satisfy 4 covalent bonds. This guy already found his spot. That may be an arsenic or antimony atom in a silicon lattice, for instance. And this is a Frankel defect where one atom is popped out, but it can pop back in just as easily. So this could have been triggered by an ion implantation that we talked about. So maybe this might be, question.
Talk about that boron moving around. It wouldn't move around under room temperature conditions, right? It would have to be heated up, or would it be doing that over time?
Temperature and time, you are right. So therefore, at a lower temperature, the diffusivity coefficient would go way down, and so therefore, yes. It would still, nothing ever stops and doesn't move at all, but it would be greatly suppressed. Yeah. So here's kind of a structure property relationship to some degree. That as the material goes to these nanocrystals, then you've created this opportunity for charging this, and this becomes your flash memory, which is hopefully recording the video of this review session on that SD card, right? And so hopefully it's storing that. Here's also non-volatile memory. And you remember those trench capacitors I showed you? That's the DRAM, right? DRAM. So then here is an edge dislocation. So this is really a misfit dislocation. So that's maybe one lattice constant on top of another lattice constant. And here, this was just stretch the bonds from this to this or this to this was just too much. And basically the covalent bonds said, no, we're not going to go there. They're like elastic bands, right? They only stretch so far, and then they break. So this guy really couldn't satisfy. And so then these guys hooked up with the nearest neighbors here, and this guy's left unsatisfied. And so recognize there are dangling bonds going into the board. That whole row of atoms has a 4th covalent bond that's unsatisfied. So that covalent bond is sitting there unsatisfied and it's wagging its tail or its ears, and it's looking for something coming by. So an impurity or something like that. So it's gonna scatter electrons. It's not a good thing usually. So you can have edge dislocations, screw dislocations. You can have all these dislocations, and you're not a material scientist. But if you are interested in this field, there are some technical electives you can take from material science. You actually learn to do transmission electron microscopy. I think it's a 2-course sequence. You take one course that's more lecture-based, so you learn the theory, and then you actually go to the lab and you actually do electron microscopy. So some of my graduate students do that as sort of their minor. So here this is looking at the grain boundaries. Again, I'm not sure I would classify this as structure property, but they're looking at the structure, and here they did a stain etch and they're just using a microscope. But you don't really know necessarily the property has changed. Probably the mobility has changed. I mean, I would surmise that the mobility of this would be superior to the mobility of this, because, is this the same magnification? It's 2 different materials. Okay, so it's apples and oranges, so I don't know. But if this was the same material, then I would surmise this is a higher mobility, because it's more crystalline, the grain sizes are bigger. Okay, so the misfit dislocation is, recognize we want to put anything on anything for maximum flexibility. So let's say you want to do blue-green LEDs or lasers. You're putting gallium nitride on sapphire. And so you have the Misfit Dislocations. And so this doesn't show where aluminum oxide is, but it's quite a large lattice mismatch. Let's maybe look at. There's another take-home problem I might have you do at some point. I don't know. I'll see how you guys handle the double diffusion. But there could be where you actually design a laser or an LED for a certain color, and you have to determine the quantum well size. You have to determine what material system you're going to use, and you have to determine what substrate you're going to put that on, and then you have to determine what the size of the layers, the thickness of the layers are that are epitaxially grown, and based on the quantum mechanics, the confinement in a finite well, you determine which wavelength that is going to determine. So you could be mixing and matching these different tie lines. But normally, we would do the classic is gallium arsenide, aluminum arsenide, and you can see how there's no strain. They're right on top of each other. So that really is beneficial. So the lattice constant of gallium arsenide and aluminum arsenide, there's no strain, no misfit dislocations there. But if I want to put indium and tinamide on indium arsenide substrate, then good luck, brother, because I'm going to get a lot of misfit dislocations. So I'm going to be limited by how much antimony I can put in before it breaks down. So this is really it. This is your Jenga towers. This is the homoepitaxy of one crystal of the on top of another, where they're the same lattice constant. So it's a homoepitaxy. And here's a heteroepitaxy. So this particular case is a larger lattice constant on a smaller, and see it. There's a deformation. It strains. It tries to accommodate, but at some point the Jenga tower pops, and you get a a row of atoms every so often, right? And so that means that this was the lattice constant was too different, and the thickness got to be too large. You know, it might have accommodated that strain if it was 1 to 2 monolayers thick, but once it got to be 3, then the strain energy was too much. So it became, the terminology I like is that it became, where is it in here? It became energetically favorable to produce a misfit dislocation to release the strain energy. That's my preferred terminology, but you can use your own words. And so here's the critical thicknesses of different materials. So this should make sense, because as you go to pure silicon on silicon, the critical thickness goes to infinity, because you're just putting silicon on silicon. And there's no limit to that. This is showing how I can look at this. This is more information than you need. Shows me that I can inspect this at the atomic level. And remember, this is something that actually showed you that misfit dislocation generation is not fiction. This is actually something I observed in first principles in the reactor during the growth. As you see the lattice constant change. So yeah. So the strain. Here's what the misfit dislocations look like from the side. This is what they look like from the top. Ways to make bulk epitaxy. So this isn't a process class, but you should kind of know where things come from, I think. And so here's the Tucholsky, and that led to the ability to make those boules and those large ingots or crystals. And so here's the Tucholsky method, and then you slice that, make the wafers, and here you can see the process in that video. Also helps, hopefully. And so you make the whole thing. and different ways. You don't have to know all these, given this isn't a process class. And then, but do know that, you know, I can modify. I can do implantation or diffusion, right? So here's diffusion, and here's implantation. What's the consequence of the diffusion? I mean, this is kind of a finer level, not really necessary for the 30-30, but you can see how the diffusion, it diffuses down and laterally. So this is less controllable. It's kind of messy, right? It's going all different directions, meaning isotropic. The implantation is more directional, but of course we get all that damage. So, but I can very precisely deliver through this railgun, you know, this ion implanter, I can precisely deliver atoms, either deep or shallow, whether they're heavy or light, you know, so we can figure that out. Okay. So we can concatenate different implantations, get different profiles. This is going to come up when we get to transistors. We'll come back to the implantation. So some of the older generation transistors, we could set the threshold voltage very precisely by being able to implant right at that famous SiO2 silicon interface that we were talking about earlier. So by being able to put that right there, that'll become very, very important. Okay. So there's ways to make devices through epitaxy. And so that could be liquid phase epitaxy here. Who's trying grow the crystals at home? How many takers do I have? 1, 2. That's it? 3? Okay. Okay. So here's the VPE and MOCVD. MBE,